Okay, good afternoon. Today I want to do an example of load line analysis. So we stopped on Friday. We introduced the topic of BJT and said this week I'm going to finish up the diodes and diode circuits. So we're going to look at the analysis technique, graphical analysis technique to analyze diode Q points or operating points. That is the load line analysis. And then we look at rectifier circuits and then Zener diodes. So that will be on Wednesday and Friday. For now, let's go into the example. So make sure. Okay. So this was the load line analysis technique. This is a graphical analysis technique. So sometimes the results are not, it depends on the system that we are using. Obviously, previously, before the advent of computers, we used to do these by hand. It's the results, so the numbers would not be precise unless we had a really large surface for a graph, and then we get some accurate numbers. Nowadays, with the advent of computer systems, we can use many analytical calculations as well as online graphs or software. Okay, so our circuit is shown right here. In the interest of saving time, I have my annotations already copied on there. So the circuit has a 12-volt DC voltage source applied to a diode via a network of 4 resistors, R1, R2, R3, and R4. Okay. So the question being asked is, what is the diode operating point? And then what is the total power supplied by the source? Okay, total power supplied by the source. So if you have signed on to the class notebook, you already have these annotations at your end available. All right, so the first thing we want to do is we want to determine what the voltage is at the terminals of the diode, right? Meaning what is the source that is being seen by the diode. And in order to do that, we need to determine the Thevenin equivalent circuit as seen by the diode. Okay, Thevenin equivalent circuit as seen by the diode. So to do that, we break up the circuit right here. In general, to determine the Thevenin or Norton equivalent circuits, you always remove that component from our analysis. When you remove components from your analysis, that leaves behind 2 open terminals. Then we analyze the circuit between those open terminals to give us one single voltage source and one single resistance. That would give us the value of the voltage being applied here. Okay. And so that's what you're going to do. So if you want to find the Thevenin resistance, you would take this circuit and we would measure the resistance at these 2 terminals. To measure resistance, we zero out all independent sources. Zeroing out independent sources would mean that the voltage source is replaced with a short circuit. So to find RTH from here, the circuit would look like this. And this would be RTH. Okay. There are multiple steps that are involved. Thevenin and Norton is a theorem. It's a very handy theorem or a very handy principle to apply to circuits to determine the actual voltage or actual current for a particular component. So RTH turns out to be 50 ohms in parallel with 50 ohms in parallel with 10, which would then be in series with the 20 ohm resistors on either side. Okay. And so that gives us 48.3333 ohms. That's your Thevenin resistance as seen by the diode. The goal, of course, is to obtain this circuit right here. So we can write an equation for the line. Okay, that's the purpose. And then VTH, to analyze for VTH, we need to find the voltage that is available between those terminals without the diode. So far, so good. Now, the 20 ohm resistors are not connected to anything. If they are not connected to anything at one end, they may as well not be part of the circuit at all. So the circuit actually looks like this. Again, this is only for analysis purposes. That's what it is. Quick recall of the theory is, if you have a resistor as part of a circuit, and one end of the resistor is open, there's no pathway for the current to flow through. So the voltage drop across the resistance is 0. If the voltage drop across the resistor is 0, that means both ends of the resistor are at the exact same potential, meaning the voltage at the connected end, voltage at the open end of the resistor is the same as the voltage at the connected end. So the voltage at this point is the same as this. And that's the principle behind it. And so you find VTH. Now we can consider these two resistors to be in series, and we can apply voltage division. When you apply voltage division principle, you obtain VTH is 2 volts. Does any of this ring a bell from EE 115? Okay. All right, so now we have Thevenin voltage at 2 volts, Thevenin resistance at 48.3333 ohms. Now we are ready to write the equation for the line. If you apply KVL to the circuit, this is ID, diode current ID, right? So diode current ID, of course, can be determined directly from the voltage and the resistance that's given to us, because it's a series circuit. So the voltage source, the resistance, and the diode all share the same current. So from KVL, we can write the expression VTH, the total Thevenin voltage, drop across the resistor voltage plus the diode voltage. From there, if you want to find 2 points of the line, we plug in ID is equal to 0. VD is the source, 2 volts. And if VD is equal to 0, then diode current ID is 41.3793 milliamps. Okay. So let's take a pause while you let all of those steps sink in. Think over that and let me know if you have any questions. Did the steps make sense so far? If you have any confusion, please let me know. Yes. So the principle would be, the question being asked is, how are they 0? So in general, let's say this is connected. If you have a resistance like this, that is connected at one end and one end is open. So this is the open end. This is the connected end. There is no pathway for the current to flow through. Any current that comes from the supply is going to go down here. Nothing's going to go here because there's no pathway for the current to flow through. If there is no current flowing through that resistor, the resistor that's open, that means the voltage drop across that resistor is 0. If the voltage drop is 0, that means that both ends of the resistor are at the exact same electric potential. So this and this point are the exact same potential. Yes. So KVL and then these, right? Okay. But did this explanation make sense to everyone? Okay. So the question now is about the 2 points. So if we go back to, let's see, let's go here. This is far better. So if you have a circuit like this, one voltage source, one resistance, one diode, which again, all circuits are not as simple as this, but we can reduce a linear circuit to this form by finding the Thevenin and Norton. And so that's what we did. We found the Thevenin and Norton, Thevenin equivalent circuit. And then in the next step is the load line analysis. So first half of the problem was determining the Thevenin resistance and Thevenin voltage. And the second part is applying the load line analysis. So for load line analysis, this is pretty standard. It doesn't matter what device it is, whether it's a transistor BJT, whether it's a MOSFET, whether it's a Zener diode, whether it's a regular diode, the load line analysis remains the same. For that, what we are doing is we are treating the entire circuit as a linear circuit because we are operating only at one single point. So at that single point, at single voltage and single current, we can treat the nonlinear device as a linear device. So we can describe that circuit as a straight line. To describe it as a straight line, we need two endpoints for the line. And to determine the two endpoints of the line, we need a value for the voltage and we need a value for the current. And the assumption would be that the line is going to intersect the X and Y axes at two different spots. The intersection points would mean, so the X axis intersection would mean Y is equal to 0. And the Y axis intersection would mean X is equal to 0. So we plug in ID is equal to 0 and VD is equal to 0 one by one to obtain the values for VD and ID. So if we plug in ID is equal to 0, we get VD is equal to the supply voltage. And then you plug in VD is equal to 0 and we obtain a value for ID. Once we have those 2 points, we can then join the 2 points and we can obtain the line. The straight line is one of the equations. The diode characteristics is the second equation. And the intersection of these two gives us the Q point or the operating point of the diode. We will do this again for Zener diode and for BJTs. But the steps remain exactly the same. You would have a linear equation or a line equation in terms of the voltage and the current. And to find the two endpoints, meaning the two intersection points, you would plug in current is equal to 0 to find voltage. You plug in voltage equal to 0 to find the current. Find the 2 points, join them, you get your line. Wherever it intersects the characteristic of the device is the solution or the operating point. Yes. Which one? This characteristic? That has nothing to do. So the question being asked is about the diode characteristics, right? This one? That's the basic diode characteristic. That has nothing to do with the external circuit. That's the internal characteristic of the device. So that is not going to change. Doesn't matter what the value of the voltage source is. It will not change with regards to the resistance. So diode characteristic would be a result. Well, diode characteristic is basically inherent to the device itself. If we plot a voltage versus current or a current versus voltage plot of the diode or for any device that matter, it's all going to be of a similar form. The only difference would be in the manufacturing. So the slight difference in manufacturing, this would be somewhere here or might be somewhere over here. But the shape would remain pretty much the same. Now, that is the diode characteristic. The line represents the external circuit. Okay, so the line represents the external circuit. So if the resistance changes or if the supply voltage changes, then the line will shift. Vs and Rs, right? Because right now Vd is equal to Vs. That's what we took. If Vs is 5 volts, the line is going to be somewhere to the left. If Vs is 10 volts, it's going to be to the right. So again, diode characteristic, device characteristic does not change. Device characteristic is actually describing the device itself. So whether it's a diode or a Zener diode or a BJT or an FET, the characteristics are exactly the same. The only thing that would change are the values of the characteristic. And then the line is describing the external circuitry. So did all of that make sense? Yes. You're talking about this slope? Okay. So now I get the question. I thought you were asking about the previous one. All right. The slope over here is exaggerated just for explanation purposes. That's all it is. No. And the scale is small. So it's only 0.6 and then it's only going up to 0.8. So the slope is exaggerated. That's all it is. Okay. So we obtained the 2 points, 2 volts and 41 milliamps. So we plot these. 2 volts is right here. 41 point where milliamps is right here. You join them. This is the line that describes the external circuit. Okay. And this is the diode characteristic that was provided to us. Remember, load line analysis is trying to solve for the diode voltage and the diode current. So there are 2 variables, diode voltage VD, current ID. We have 2 variables and we want to solve them. We need at least 2 equations. So if you're performing a graphical analysis, one of the equations is the diode characteristic. The second equation is the line. The intersection of those 2 give us the solution or the operating point. Extrapolation of that point to the x-axis and the y-axis gives us the value of the diode voltage and current due to the 12-volt source. That comes out to be 1 volt right here. That's VD or VDQ, diode voltage at the Q point. And this 21 milliamps is IDQ, diode current at the Q point. Okay, at the Q point. Let's take a pause. Let me know if you have questions. Yes. Q point is the value of the device quantities based on the external circuit. So the question being asked is, what exactly is the Q point? It's kind of an important question. Q point is the value of the device due to the DC applied voltages. It is basically setting up our device to operate within some constraints. Okay. So the external circuit, so whether it's a diode or any kind of device. If you perform the lab today, we work with BJTs. We apply DC voltages. When you apply DC voltages, we are forcing that BJT to operate within the parameters of that circuit. So the same thing happens here. We have an external circuit, you have an external power supply. We are forcing the diode to operate within a certain portion of its range. Okay. So this load line analysis, the operating point is the constraint placed on the diode by the external circuit. So this point depends on the supply voltage and the resistor connections that are present in there, because those resistors and those connections determine how much voltage is being applied to the diode. As practice, what you can do is change the supply voltage. You change the supply voltage from 10 volts, you can go down to like 5 volts. What is it, 10 volts? Yeah, 12 volts, sorry. From 12 volts, you can go down to like 10 and 5 volts. And you can also go up from 15 to 20 volts. Just run through the numbers. It'll take you probably like less than 5 minutes. You already have the equations. Simply plug in Vs is equal to 5, 10, 15, and 20. Find the other 2 points, and you will see that your line would shift like this. Either down or it will shift up. Obviously, if you're applying Vs is equal to 20, well, you'd have to calculate, sorry. You'd have to calculate the Thevenin voltage. Again, you have all the equations, so you'd be able to calculate the voltage. Anyway, the point being, you change the supply voltage to 5 volts, to 10 volts, to 15 volts, and to 20 volts. Your Thevenin voltage would change. Simply plug in the numbers, calculate those, and then find those 2 points right there. The voltages and the currents. So in response to the external supply, that Q point is going to shift either up or down the diode characteristic. Okay. So again, if we want our diode to operate at say 1.2 volts, let's reverse engineer, right? Because as an engineer, that's what you'll be doing. You have a goal in front of you. You have to reverse engineer and go to the beginning. So if you want your device to operate at 1.2 volts, you can find the intersection point somewhere right here. So you have VD, you have ID. Now determine what voltage value would be required from the battery, from the original supply. Does that make sense to everyone? So again, load line analysis, and specifically I'm spending some time over here because we're going to use this again for Zener diode. We're going to use it again for BJTs. We're going to use it again for CE amplifiers. It's a very useful technique, but the steps remain the same. You take your circuit, reduce it to one single voltage source and one single resistance, apply KVL, you obtain a linear equation in terms of the voltage and the current, plug in both as equal to 0 in turn, and then find the other quantity. And then you have your operating point. Okay. Again, operating point is the constraint placed on the device by the external circuit. Right. All right, we have time for a few more questions if anyone has. Well, actually, we need to get through this and I've almost out of time. Okay. My annotations and calculations are all here to determine the power. So please review those and then, well, review those, prepare your questions, and I will go over that and you answer your questions on Wednesday. All right. So we'll end class here today, and I will see you all on Wednesday.